Greetings to the respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951 and 86. And today I'll be presenting on the topic DeepGal, an intelligent vehicle control for traffic congestion alleviation at intersections as a part of the course computer network. Traffic congestion is one of the most serious urban challenges today. Intersections are the primary congestion points where traffic streams conflict and delays accumulate. Traditional signal systems operate on fixed timing schedules that cannot adapt to real time conditions, resulting in inefficiency and wasted fuel. DeepGal represents a shift from reactive, reactive traffic control to intelligent, network driven coordination. Instead of treating vehicles as isolated entities, DeepGal treats them as connected agents that communicate and cooperate. This presentation focuses on how networking infrastructure enables intelligent traffic systems and how coordinated communication can transform congestion into optimized flow. Modern cities suffer from increasing traffic density, leading to delays, pollution, and economic loss. The root problem is not only the number of vehicles, but the lack of coordination between them. Traditional traffic lights assume predictable traffic patterns, but real world traffic is dynamic. Accidents, weather, and unpredictable human behavior constantly changes conditions. Computer networks enable vehicles to share real time information about position, speed, and intent. This communication allows intelligent algorithms to coordinate movement instead of relying on rigid rules. DeepGal uses networking and deep learning together to create adaptive traffic control. It demonstrates how communication infrastructure can transform transportation into a cooperative system. Intersections are complex negotiation points where vehicles from multiple directions compete for access. Fixed scheduling forces vehicles to stop even when the road ahead is clear, creating artificial bottlenecks. Stop and go behavior increases fuel consumption, emissions, and driver frustration. It also reduces intersection throughput. Human drivers operate independently without coordination. Even when cooperation would improve flow, lack of communication prevents optimization. DeepGal addresses this by turning intersections into coordinated multi agent systems. Vehicles communicate to plan safe and efficient crossing sequences, minimizing unnecessary stops and maximizing flow. Intelligent transportation systems. Intelligent transportation systems combine sensing, communication, and control technologies to maintain traffic in real time. Vehicles act as mobile network nodes exchanging data through vehicle to vehicle communication. Infrastructure units act as coordination hubs through vehicle to information infrastructure communication. This network forms a distributed computing platform embedded into the road system. Decisions are no longer centralized or fixed, they are dynamic and collaborative. DeepGal is built on its foundation. Its leverage it leverages the communication network to enable intelligent decision making at the intersections. Computer networks are the backbone of DeepGal. Without fast and reliable communication, coordinated vehicle control is impossible. Vehicular networks must support ultra low latency because decision affects safety. Messages must be delivered in milliseconds. The network topology is highly dynamic. Nodes constantly enter and leave range. Routing protocols must adapt instantly. Reliability is critical. Packet loss or delay can disrupt coordination and lead to unsafe conditions. Thus, DeepGal relies on thus DeepGal DeepGal relies on advanced networking principles such as real-time communication, decentralized coordination, and fault tolerance. DeepGal is a deep reinforcement learning framework designed to coordinate vehicles at intersections. Each vehicle acts as an intelligent agent that learns optimal actions based on shared information. Instead of obeying static signals, vehicles negotiate crossing orders dynamically. The algorithm minimizes congestion, waiting time, and collision risk. DeepGal transforms traffic control into a multi agent learning problem where cooperation replaces competition. Networking enables agents to use state information and align decisions. DeepCal architecture is a distributed multi-agent system. Each vehicle runs a neural network that predicts optimal movement based on local and shared data. The intersection acts as a coordination environment rather than a controller. Agents exchange information through the vehicular network and update decisions continuously. DeepGal depends on a robust communication model built on vehicle to vehicle and vehicle to infrastructure networking. Vehicles constantly broadcast their position, velocity, and intended trajectory to nearby nodes. The shared state allows all agents to predict movement and coordinate safely. The communication model must operate in real time. Even small latency increases can break synchronization and reduce system effectiveness. Therefore, DeepCal requires ultra reliable low latency communication similar to the requirement of 5G vehicular networks. DeepCal reduces congestion by replacing stop and go patterns with a coordinated flow. Instead of traffic lights forcing vehicles to wait, agents dynamically negotiate crossing sequences that minimize delay. Vehicles adjust speed smoothly rather than stopping completely. This reduces energy waste and improves throughput. The algorithm predicts conflicts before they occur and resolves them through cooperative scheduling. From a systems perspective, this is similar to packet scheduling in computer networks. Just as routers manage packet flow to prevent congestion, DeepGAN manages vehicle flow to optimize intersection performance. Deploying DeepGAL introduces significant networking challenges. Vehicular networks are highly dynamic environments with constant topology changes. Nodes appear and disappear rapidly as vehicles move. Packet loss is a serious issue due to wireless interference and congestion. Safety critical systems cannot tolerate unreliable communication. Redundancy and error recovery mechanisms are essential. Latency must remain extremely low. Delayed information leads to outdated decisions, which can reduce safety and efficiency. Scalability is another concern. As traffic density increases, the network must handle more simultaneous transmissions without collapse. Security also becomes critical. Malicious actors could inject false data to disrupt coordination. Therefore, authentication and encryption are necessary components of the network design. When networking works correctly, DeepCal produces measurable improvements. Average waiting time decreases significantly. Intersection throughput increases because vehicles move continuously instead of stopping. Fuel consumption drops Fuel consumption drops due to smoother acceleration patterns. Emissions are reduced, contributing to environmental sustainability. Drivers experience less frustration and more predictable travel times. From a networking standpoint, DeepCal demonstrates how communication infrastructure can directly influence physical systems. It proves that intelligent coordination enabled by networking can produce real world efficiency gains. DeepCal is evaluated using traffic simulation environments combined with network simulators. These simulations model realistic vehicular communication delays and packet loss. Performance metrics include average delay, throughput, collision risk, and network load. Results consistently show that DeepCal outperforms traditional signal based control. Future development of DeepCal in, involves integration of 5G and edge computing. High speed networks will reduce latency and enable faster coordination. Edge computing allows decisions to be processed near intersections rather than in centralized servers. This improves response time and reliability. Another, another direction is mixed traffic environments where human driven and autonomous vehicles coexist. Algorithms must adapt to unpredictable behavior while maintaining safety. Enhanced security frameworks will also be necessary as intelligent transportation becomes critical infrastructure. In conclusion, DeepCal demonstrates how computer networks can transform traffic systems Intersections become cooperative distributed systems instead of rigid mechanical controls. The key insight is that networking is not just about data transfer. It enables coordination between intelligent agents. Reliable communication also allows vehicles to function as a synchronized system. As cities move towards smart infrastructure, the integration of networking and AI will redefine the transportation efficiency. Thank you for your attention. This presentation showed how DeepGal combines networking and artificial intelligence to reduce traffic congestion and improve urban mobility. Intelligent transportation is not only about transportation problem, it is a networking problem. The future of smart cities depends on reliable communication systems that enable cooperation at scale. Thank you.